Hi guys, welcome back. Today, in case you missed class, I am doing over one of the labs that we did in class today, or we were doing an energetics lab calculating the heat of solution for sodium chloride. So when you go in the lab manual, you're gonna see this lab written up in it, right? So this is a lab that I am doing, and we did put in some values, but now I'm doing it over. So this table would be blank. So this is how you'd see the table in the lab in your lab manual. Perfect. So we're gonna go ahead and open up our virtual chemistry lab. Right. So we go to this site, Chem Collective, and we just click on virtual lab over here, and it takes us to our virtual lab. So I'm gonna wait for it to load. Right, so I'm a little bit impatient, so took too long to respond, but it is working. Let me just refresh it. Alright, so see it's loading. If you go on the site, sorry, it's not working, just give it some time. Alright, so let's go back and read the instructions a little bit. We're going to measure a certain amount of water. So I already decided that we're using 50 ml of water, and we're going to be using 10 grams of sodium chloride. Now, be sure to change the solid in the lab manual to fit the video or whatever you're using. So because we're changing sodium chloride, I ensure that I change the name to sodium chloride because that's what I am measuring for. Good. And I just fix up my method and everything. I double check my method. So this is one of the things that you should do, and double check for all the things, the apparatus that you're using. Of course, I'll be marking for that. Now, the apparatus that I'm gonna be using for this lab is I'm going to be using some glasswares. I'm going to be using at least two beakers. I put them out, and I'm going to be using a granulated cylinder too, and I am going to be using a scale. Now oops, you can only use a certain amount at a time, a certain amount of things. If you put too much, you just right click and take it off back. I need to measure out some distilled water. So now proper etiquette says that you cannot just put the granulated cylinder. The cylinder is too small, so I'm gonna remove it. I'm going to be I need a bigger cylinder, a bigger granulated cylinder. I want to measure about 50 grams, I was saying, so I'm gonna change my method to 40 gram. Don't want to measure to the exact amount that the apparatus can use. So you see, I'm changing it to 40. Share this tab instead. So I'm measuring out 40 grams of water. So I wouldn't just take the granulated cylinder and put it to the big what we store the water in like that. First I would take it and pour it into a little beaker. So I don't need to measure out this. I can just go ahead and pour. Alright, so you see I pour out some. Good. Actually pour more than can technically hold in the beaker, but it wouldn't overspill yet. Now I'm going to take the beaker and rest it on a flat surface, and then I'm going to take the take the granulated cylinder, rest it on a flat surface, take the beaker, and I'm going to measure out precisely 40 ml of water. So you see, I put precise, put in what I want, press pour. Now look at the meniscus. When we're measuring, we need to ensure that the bottom of the meniscus is touching the line, and we're setting our eye at eye level to the bottom of our eye is on the same level as the meniscus to prevent parallax error. Good. So now I have my granulated cylinder with my water. I can actually get rid of my beaker and my storage, the storage container for my distilled water. I need to collect my solid, and my solid is going to be sodium chloride, right? So now it's time to prepare the solid. I'm actually gonna be recording myself so I can watch back the video and see the lowest time. Now I'm preparing the solid. I'm taking my beaker and I'm placing it on my balance. Now look, this is the mass of the balance on the beaker. It's 104 degrees Celsius. Don't want that mass. So I'm just gonna tear it off. Press tear. Not sure what's happening, but when I press tear, it should zero the scale. Alright, so straight away, this is a error happening in the lab that I could prevent. So this is limiting my research right now. So I'm going back again. I'm getting a next scale, one that's working properly. Put on the beaker. See, same 105.77 gram for the beaker. When I press steer, now you can see the balance working properly. Getting rid of that. Now I'm going to measure out how much. I said I would use 10 grams of the sodium chloride. So I'm going to measure that on the beaker. That's how much I take out. And wow, I am measuring properly because look on the scale. It now says 10 grams. Perfect. So I'm going to take the sodium chloride and remove it from my workbench now because I don't no longer need it. In my beaker, which I can rename, I have NaCl 10 grams. So I have NaCl in my beaker 10 grams. You know, it's very important to label when you're going ahead and doing the lab. In this measuring cylinder, I have my water. And not just any water, but my distilled water. I'm just assuming that this is very, very pure water so that it will not be affected by nothing else is dissolving the water. It's just pure water I'm using now. Now, first thing I want to do is go ahead and check the temperature of my water. Right here you can see I have a digital scale and it tells me that the temperature is now 25 degrees Celsius. So that's the starting point. And I'm going to go back in my lab manual and write down that starting point. My initial temperature is 25.00 degrees Celsius. That's very important to write down the starting temperature. Now I am going to go back to my virtual lab and I am going to pour this distilled water in my beaker and record the highest temperature. Now since I'm at home and this is going to go very, very fast, I'm also using my phone to video. So I can see I can watch back the video really quick and see the temperature change. So I start the video on my phone and I pour in my distilled water. Remember, we had 40 grams, so I'm pouring all of it into my beaker. Now I'm recording the highest temperature change, the lowest or the highest temperature change. Sorry. So the water temperature went down and now it's coming up back. And I can't stop now. So I'm watching back over my video to see what's the lowest change I can see on the video. The lowest change. The highest temperature change, the lowest or the highest temperature one, and I pour in my distilled water. Remember, we had 40 grams, so I'm pouring all of it into my beaker. Now I'm recording the highest temperature change, the lowest or the highest temperature in my distilled water. Remember, we had 40 grams, so I'm pouring all of it into my beaker. Right, so I recorded it, I captured it. The lowest temperature change I can see from the video is 21.10. So it went all the way down to 21.10 degrees Celsius. Really happy with that mark. We can see that indeed there was some temperature change. And it's not 21.0 flat, you know, it's 21.10 degrees Celsius change. So I'm just accounting for that right now. Perfect. So I have my initial volume and my final volume. Now to record my temperature change, which we call delta T. So delta T, which is my temperature change, that's the symbol for it. Carry it down a little bit. Delta T equal to 25.00 minus 21.10 degrees. So I have a temperature change of 3.9 degrees Celsius. So the final temperature minus the initial temperature gives me negative 3.9 degrees. So that is it now. Final temperature minus initial temperature. So Ft minus TIT. That gives me negative 39 point, negative 3.9 degrees. And we're happy to proceed with that. Alright, so that's it for the lab. Now it's time to do my calculations. Now I need to calculate the heat change in the reaction, and the heat change is Q equal to MC delta T. So my heat change is MC equal delta T. So I'm going to write down what M is. M is the mass of my water. And from the method, I go back into the method. Remember, I use 40 ml of water. I use 40 ml of water. The mass of water given 40 ml was used. So what I'm gonna do is assume that 1 ml equal to 1 gram. This means 40 grams of water was used. This means 40 grams of water was used. So I found my M just by making some assumption that is very common to these calculations. Good. Next thing, I am going to go ahead and find my specific heat capacity. C. I am going to assume that the specific heat capacity is the same as that of water. I'm going to assume that the specific heat capacity of the solution is the same as that of water. What this means, water specific heat capacity equal to 4.2 joules per gram per degree Celsius. So this is my specific heat capacity of water. Alright, so I found what my C is. So C is equal to that of water. I can just write C equal to that. Now, what is my temperature change? I calculated it up here. So I am ready to use my formula Q equal M C delta T. I know what M is, I know what Q is, I know what the heat change is. So my mass was again the mass of my water, which is 40 grams. Going to multiply that by delta C, which is 4.2 kilojoules. And then I'm going to multiply that by my heat change, which we calculated to be negative 3.9 degrees Celsius. Good. So this is what I'm going to be using. Now, you know me, I like to set out my questions so my units can cancel. So that's what we're going to be doing right now. I'm just going to rewrite this so I can see my units and cancel it out when necessary. All right, so starting here. So 4.2 gram, put in the times 4.2, that should be gram, and we have degrees Celsius down there too. Oops, sorry. Degrees Celsius. So that is what it means. Per means I have 4.2 Kelvin divided by that. All right. Now I'm going to be timesing that by my heat change, which was negative 3.1 degrees Celsius too. All right, so what's happened? I have this. Let me write it back again. This is the unit set out. What this means is that I have grams at the top and grams at the bottom. So this gram can cancel gram into itself, and this gram can cancel also because I have it at the top and I have it at the bottom. Look, we have Celsius at the top and it's also in the denominator. That means we can cancel out the Celsius. Perfect. So now the units for my answer left back is only joules. This means that the specific heat capacity is measured in joules. Perfecto. So now I have 40 times 4.2, 4.2 joules times negative 3.9. And when I work out that, my answer is going to be 40 times 4.2 times 3 negative, times negative 3.9. My answer is negative 655.2. So that's my answer right there. And not, don't forget the units, joules. Now I have it in joules, but I need to convert from joules to kilogram. What need to move from joules to kilojoules? Sorry, joules to kilojoules. What I'm going to do is say, I know my ratio joule, 1 joule equal to, sorry, 1 kilojoule, 1000 joule equal to 1 kg, kilojoule. All right. Notice how we write it capital K, common J. So I'm gonna apply that logic to this now. I have negative 655.2 joules. Multiply that by my ratio. Mean I have joules at the top. That mean I'm gonna have 1 kilojoule at the top, and then my joules are going to be at the bottom. What's gonna happen? This is going to, joules and joules will cancel. So joules and joules will cancel. Joules and joules will cancel. So I am going to get negative 655.2 kg divided by 1000. And jump 2 space, that's going to give me 6.5 equal to 6.55 kg. Wait, sorry, 3 spaces are going to move to the left. So it is 0.6552 kg. Good. So I insert that now. So I know that my heat change is this value that I just calculated. Perfect. So now, right, so I only need one of those pictures. Now I need to go ahead and calculate my heat of solution. My heat of solution equal to Q divided by number of moles. So Q divided by number of moles of solid. Heat, heat change of solution divided by the number of moles of solute. What is my solute? Well, my solute that I used was my sodium chloride, and I used 10 grams of it. 10 grams of sodium chloride was used. How do we move from grams to moles? Once again, this is easy, and we just apply our conversion factor, which I won't be doing, but I want you guys to do it. I have 10 grams of sodium chloride, NaCl, NaCN, 10 grams. And I need the RMM, which is the molar mass of the sodium chloride. That's going to give me 1 times 23 plus 1 times 35.5. That's going to give me a total of 23 plus 35.5. That's going to give me 58.5 grams. 58.5 grams per mole. So my mass is gonna be equal to given mass. Well, my mass, when I work it out, put in my conversion factor from mass to moles, I'm going to get my answer to be 0.17 moles. So 0.17 moles was used. So I did end up calculating my number of mole. Sorry, number of mole equal to 0.17 mole. And I did skip out a calculation here because you need to know how to convert 10 grams of NaL to moles. What we need for the conversion is the molar mass. We need the molar mass and we need the given gram, which was 10 grams. Set it up so that your mass cancel because you're trying to get rid of that and you get the mole. I expect to see the setup in your lab book, guys. Now, what do we do next? To find the heat of solution, we say 0.17 moles gives off 0.655. That's what we had. Kilograms. 0.6552 kilograms. Given moles equal to 0.552 kg, right? So 1 mole equal to, we don't know. So when I set it up like this, I just using the unitary method. What that mean, I have my 0.6552 kg. I'm going to divide that by the number of moles, which was 0.17 moles. So I can put that in my calculator, and when I get my answer, I write it down as the heat solution that we found. So my answer for the heat of solution equal to 3 3 sorry equal to 3.85 kg per mole. And I'm just going to make a note that I recorded this to 2 decimal places. So 2 dp. And insert my maths right there. Even when I was calculating the moles, guys, I put that to 2 decimal place also. Let me fix this. 2 decimal place. That's what dp mean. No, it's kind of important to tell how much decimal place you put your stuff to. So this is 0.17, which is 2 dp as well. So I'm just going back and ensuring that all my units are there when they're supposed to be there. And if I did any rounding off, I am writing what I round off to. So this one, let me edit it. I just gonna double check. 6 point negative 6, sorry, 40 times 4.2 times 3.9. Alright, so I didn't do any rounding off. It just gave me that exact answer. Alright, so everything looks good. And I did my calculation. Now I need to say whether this is an endothermic reaction or this is a exothermic reaction. Oh Lord, I forgot a little bit of something right here. Let me edit it. Notice the negative sign, it's very important. Don't do the work and forget to put in a negative sign where it's supposed to go. That's gonna be bad because my heat of solution is negative. You notice how that affect my answer negative? It gave me the wrong answer. Heat of solution is negative. That means energy was lost to my environment. My heat change should also be negative. So don't forget to put in your negative signs. Jeremiah, can you leave for me, please? Thank you. Oops. I don't want to insert the math in. I'm trying to delete something. Let me just press undo. Right, so this math, I want to edit it. I might have to write it over because it's telling me that I have a positive heat of solution, which is wrong. If you're supposed to have negative and you write positive, you're going to get your answer wrong. So insert my math. I'm actually going to rewrite this properly because you notice because we were doing the calculations. Because we were doing the calculation in the equation up actually, it changed my units. I don't want it to be set out that like that. I'm just gonna rewrite it as 3.85 kg mole, and I'm gonna raise it to the -1 power. That's how we kind of write the units properly. Perfect. So this is the heat of solution that I calculated. So actually this question right here is redundant. The heat of solution, I calculated it. That is it. Is my reaction endothermic or exothermic? I'm gonna leave you guys to do your readings and you guys can tell me next class if you believe my thing was exothermic or endothermic. Did I encounter any problems while doing this lab? Yes. One problem I encounter, if you can remember, the balance was not properly calibrated. So I had to repeat the experiment using a different balance. So that's one limitation. Oh wait, you're not supposed to write I, Lord Jesus. The balance was not properly calibrated. So I'm fixing it up now. So it gave incorrect readings. Full stop. Hence, the experiment had to be repeated using a different balance. So that's one limitation that we had in conducting this experiment. I gave you 3 assumptions while doing this lab and while doing our calculations. State any 3 of them and you get your full marks. I explained the limitation while conducting this lab. While you're doing the lab, you can write your own limitations. You can go ahead back on the website, collective chemcollective.org /VL lab /VL /VLab.php. The link will be provided in the description box of this video. Thanks for watching. I hope this was informative, and I'll see you guys next class. Bye.